Planes fly within Earth's atmosphere, so we need to understand its composition and properties in order to properly calculate the capabilities or design range of an aircraft within the atmosphere. Earth's atmosphere is comprised of a mixture of gases, including primarily nitrogen and oxygen. The atmosphere sustains life on Earth and protects the surface from solar radiation. The atmosphere is a relatively thin sheet. To put this in perspective, imagine the thickness of a sheet of plastic wrap around a basketball. That atmosphere is made up of a number of layers with different temperature and pressure characteristics. The troposphere is where we fly. Troposphere comes from the Greek word trop, which means turn or change. The troposphere varies from surface to approximately 36,000 feet and by location and season. The tropopause is above the troposphere and is a level rather than a layer. The tropopause acts as a lid for water vapor, which causes weather phenomena. The stratosphere is the same composition as the troposphere and continues up to about 160,000 feet. Sometimes commercial aircraft will fly in the lower range of the stratosphere. This figure illustrates some of the machines that operate at each level of the atmosphere. The mesosphere and thermosphere are above the stratosphere. Planes do not fly up at that altitude, but later in the year we will discuss satellites and rockets which will need to operate in and pass through these layers. Air pressure refers to the force exerted on a surface by the air above it as gravity pulls it to Earth. Standard pressure is 101.3 kilopascals or 14.7 psi, which is the average air pressure at sea level at 15 degrees Celsius. To put this in perspective, the column of air sitting on two thumbnails up to the top of the atmosphere at 97 kilometers or 60 miles is 6.7 kilograms or 14.7 pounds. The density and pressure of air is higher closer to the ground. This is what people mean when they say there is less air at higher altitudes. The density or amount of air per unit area is less. Engineers will compare measurements at various altitudes to standard conditions at Earth's surface. The standards are 101.3 kilopascals at 15 degrees Celsius and 14.7 psi at 59 degrees Fahrenheit. The formulas we will use for calculating the change in temperature and pressure with altitude will be in metric units, so it will be important to remember the number 101.3 kilopascals and 15 degrees Celsius. Interestingly, the speed of sound changes with air temperature and pressure. Therefore, the altitude of the aircraft impacts the speed of sound. In Earth's atmosphere, there is a 2 degrees Celsius drop for about every 1,000 feet or about 305 meters of elevation gain. This is called the lapse rate, the decrease in temperature and pressure as altitude increases. The standard temperature T and pressure P at sea level serve as a common reference point. The temperature and pressure obviously are not always these values in actual existence. So we will use equations to calculate the change to temperature and pressure from the standard, and you will see these standard values built into the equations. Temperature T is 15 degrees minus 0.00649 times height in meters. Pressure P is 101.3 kilopascals multiplied times the temperature to a power of 5.256. Notice the portion in brackets is using the temperature calculated with the equation above and converting it into Kelvin. From these values, the atmosphere decreases in temperature and pressure following these equations as the altitude increases up to the top of the troposphere. Beyond this level, the atmosphere does not behave linearly. The lapse rate is particularly important to engineers because aircraft performance is greatly impacted by temperature and pressure. Engines and lift generated by the wings are two examples since both use air as a working fluid. Air density is affected by pressure and temperature, so as the temperature and pressure change with altitude, so does the density. Density, expressed by the variable Greek letter rho, is the pressure divided by 0.2869 times the temperature, again converted to Kelvin. With these three equations, given the altitude, the temperature, pressure, and air density can be calculated. Mount Everest is at 8,848 meters, which is a similar altitude to the cruising range of a jet aircraft. Climbers must acclimatize to the elevation or bring supplemental oxygen. Acclimatization is the process where the body adapts to a new environment. The process is dependent upon the change in elevation ranging from days to months. Each person or community has different physiology and lives at different elevations. Take a moment to use the equations for temperature, pressure, and density to determine these values at the top of Mount Everest, assuming standard conditions at sea level. With most commercial aircraft flying high above people's acclimatized altitude, pilots must react quickly if there's a pressure drop within the cabin. We'll learn more about flight physiology later, but people can begin to experience effects of oxygen deprivation or hypoxia within 15 seconds of the drop. This could mean serious injury. Pressure loss can be caused by leaks within the fuselage or even window failure. As we discussed in the last lesson, as an aircraft moves through the air molecules near the aircraft are disturbed and move around the aircraft, which helps to generate lift. However, this motion can also cause effects to the air. If the aircraft passes at a low speed, typically less than 250 miles per hour, the density of the air remains constant. But for higher speeds, some of the energy of the aircraft goes into compressing the air and locally changing the density of the air. This compressibility effect alters the amount of resulting force on the aircraft. The effect becomes more important as speed increases. Near and beyond the speed of sound, about 330 meters per second or 760 miles per hour, small disturbances in the flow are transmitted to other locations. But a sharp disturbance generates a shock wave that affects both the lift and drag of an aircraft. You can see in the image the ripple effect of the plane on the surrounding air. This transition creates shock waves and sonic booms. NASA provides a shockwave simulator to model the effect of the sharpness of the body and Mach number. You can read more about this and find the simulator on NASA's website. At one point, people thought traveling beyond the speed of sound was impossible. This photo was taken off the coast of Busan, South Korea, July 7, 1999. An FA-18 Hornet assigned to Strike Fighter Squadron 151 breaks the sound barrier in the skies over the Pacific Ocean. Now we know that traveling beyond the speed of sound is possible, we started to invent aircraft to go faster and faster. The term for traveling at the speed of sound is called Mach 1. Anything below this is called subsonic. Objects traveling from the speed of sound up to 5 times the speed of sound, or Mach 5, are called supersonic. Hypersonic is between Mach 5 and Mach 10, and high supersonic is between Mach 10 and Mach 25. For reference, upon re-entry into the atmosphere, a space shuttle is traveling at Mach 24 to 25. Can you imagine the forces acting on those astronauts? Speed of sound changes with air temperature and pressure, therefore the altitude of the aircraft impacts the speed of sound. These terms and distinctions are important to know as they may be on the end of course assessment. Here are the references for additional information. You can see the NASA website link for that simulator if you're interested.